Welcome to AR Maths Pro Learning Academy. In this video, I'm gonna talk about relations and functions of class 12 mathematics CBSE. Exercise 1.1, explanation and solutions of all questions. These are our last questions that I have given you an assignment to finish it up. So the answers are going to be like this. The first relation, it is symmetric transitive, and the second one is none of all the three. Third one only transitive. Fourth one is all symmetric, reflexive and transitive. Fifth one only reflexive. Sixth one all reflexive, symmetric and transitive. Question 1. Determine whether each of the following relations are reflexive, symmetric and transitive. The first question. Set A has 1 to 14 elements defined by a relation R equal xy such that 3x minus y is equal 0. Now, given relation is R equal xy such that y equal 3x, which is in the set builder form. Now, I want to write this in roster form. Okay, check. If I plug in the values of x here, it will be 3 times 1, it will be 3. If I plug x as 2, it will be 6. If x as 3, it will be 9. If x as 4, it will be 12. I can't keep x as 5 because if I keep x as 5, the y term is gonna be 15, which is not under set A. That is why I stopped here. So this is relation R. Now we need to check reflexive. Is it reflexive or not? Okay. So we know the definition of reflexive. For any A belongs to A, then A comma A belongs to R, which means all ordered pair with identical elements must be there in the reflexive. Now, if I check the first term, 1, 1 is not there. So I don't need to check for the other elements. 1, 1 is not there. That's more than enough. So it is clearly observed that A comma A does not belong to R for any A belongs to R. So it is not reflexive. Now, come to second part, symmetric. Is it a symmetric? Now, the definition of the symmetric says if A comma B belongs to R, then B comma A must be belongs to R. Now, if you see this relation, 1, 3 is there, but 3, 1 is not there. 1, 3 is there, but 3, 1 is not there. So it is not symmetric. I don't need to check for the other ordered pair. Just one ordered pair is more than enough. If it doesn't satisfy with the symmetric condition, then it is not a symmetric relation. Hence, it is not a symmetric relation. Now, the third part, transitive. We know transitive. The definition of the transitive says if AB belongs to R and BC belongs to R, then AC must be belongs to R. Let us check. 1, 3 is there and 3, 9 is there. 1, 3 is there and 3, 9 is there. 1, 3 belongs to R and 3, 9 belongs to R. But if I see the relation, in the relation 1, 9 is not there. But 1, 9 is not there in the relation. So the given relation is not transitive. Question 1, part 2. Relation R in the set N of natural numbers defined as R equal xy such that y equal x plus y and x less than 4. Now, given set N is nothing but all natural numbers from 1 till infinite. Natural number starts with 1. Okay. Now, and the relation R is defined on set A as xy such that y equal x plus y and x less than 4. Which means I got the relation in the roster form like this. If I keep x as 1, y is 6. If I keep x as 2, y is 7. If I keep x as 3, y is 8. I cannot keep x as 4 because in the condition it is given x must be less than 4. So this is my relation now. Now I need to check symmetric, reflexive, symmetric and transitive. The first, reflexive. We know the definition of a reflexive. For any a belongs to R, then a comma a belongs to R. Then ordered pair with all identical elements must be belongs to R. Now, if you see the relation, 1 is there, 1 comma 1 is not in my relation. So I don't need to check any other ordered pair. 1 comma 1 is not there. That's all. So for it is clearly observed that a comma a doesn't belongs to R for any a belongs to R. It is not a reflexive. Now check for the second one. Symmetric. Symmetric definition says if a comma b belongs to R, then b comma a must be belongs to R. Now, if you see the relation, 1, 6 is there, but 6, 1 is not there. As 1, 6 belongs to R, but 6, 1 doesn't belongs to R. So it is not a symmetric relation. The third part, transitive. We know the definition of a transitive. If a comma b belongs to R and b comma c belongs to R, then a comma c must be belongs to R. Okay. Now see here, in this question I need to check it one by one. Each ordered pair I have to check. The first ordered pair is 1 comma 6. Okay, 1 6 is there, but 6 1 is not there. So I don't need to check the third ordered pair. For example here, if AB belongs to R but BC doesn't belongs to R, so I don't need to check AC. So this is a transitive relation. This ordered pair satisfies the transitive relation. Let's check the second one. 2 7 is there, but 7 2 or 7 some other element is not there. So I don't need to check the third part. This is also satisfies the transitive relation. Okay, the third part. 3 8 is there, but 8 something is not there. 8 is not there. 8 4 8 5 something is not there. So 3, so I don't need to check something 3 or something. So this ordered pair 3 comma 8 satisfies the transitive condition. So the given relation R satisfies the transitive condition. Hence it is a transitive relation. Question 1 part 3. Relation R in the set A equal 1 2 3 4 5 6 and R is defined as x comma y such that y is divisible by x. Try to understand, divisible means you should get a whole number. Which means, for example, if I say 5 over 3 is not divisible. It's not divisible because I'm getting the answer in decimal. So it must be a whole number or any integer. The result must be any integer, positive or negative. Then only it is divisible. Otherwise it is not. So given relation R equal xy such that y over x is equal n, where n belongs to z. Z is nothing but integers. Okay. Now, so this is in the set builder form. I need to write in the roster form. So check R equal, check R equal 1 1. Why I'm writing 1 1? Because y divided by x. So 1 divided by 1 is possible. The result is 1. So 2 over 1. Yes, the result is 2. 3 over 1. 4 over 1. 5 over 1. 6 over 1. All these are divisible. Now, if I say 2 3, which is not possible. So I cannot write 2 3 as an ordered pair in this relation. Can I write 2 4? Yes, because 4 divided by 2 is possible. Can I write 2 over 2? Yes, because 2 over 2 is 1. 2 over 6, which is 3. Now I can write 3 over 3, but I cannot write 3 comma 4 as an ordered pair because 4 over 3 divisible is not possible. So I can write 3 over 3 and 3 over 6. 3 over 3 and 3 over 6. Now 4 over 4 is possible, 5 over 5 is possible, 6 over 6 is possible. Only these 3 ordered pair are possible. So this is the relation in the roster form. Now we need to check symmetric, reflexive, symmetric and transitive. We know the reflexive. For any A belongs to A, then A comma A must be belongs to R. So check. 1 1 is there, 2 2 is there, 3 3 is there, 4 4 is there, 5 5 is there, 6 6 is there. Yes, the reflexive definition says all ordered pair with identical elements must be in the relation. This is an obligatory part. The rest of the ordered pair, it can or it cannot be. But these ordered pair must be in the relation. Then only it is a reflexive. So it is a reflexive relation. Okay? It is a reflexive relation. Now we need to check symmetric relation. We know the symmetric relation. If AB belongs to R, then BA must be belongs to R. So check 1 1, all ordered pair with the same identical element satisfies the symmetric conditions. So I need to check one by one. 1 2 is there, 2 1 is not there. Check 1 2 is there, but 2 1 is not here. 2 1 is not here. If 2 1 is not here, I don't need to check any other ordered pair. This is not a transitive, a symmetric relation because 1 2 is there, but 2 1 is not there in my relation. So it is not a symmetric relation. Now we need to check transitive relation. Okay, this is the given relation in set builder form, and this is the relation what we got it in the roster form. Now we need to check this transitive condition. We know the transitive condition. If AB belongs to R and BC belongs to R, then AC must be belongs to R. This is the condition. To check one by one, it will take a long time. So it is better to write some statements to verify our condition, transitive condition. Assume AB belongs to R and BC belongs to R. If AB belongs to R, then B over A, according to the definition, xy belongs to R, y over x is equal some integer n. Okay. Similarly, if AB belongs to R, then B over A equal M, or B is equal MA, like this one. From the definition, of course, from the definition. If xy belongs to R, then y equal NM. Similarly, I wrote AB belongs to R, then B equal MA. And BC belongs to R, then I write C equal NB for some N and M integers. Okay, which must be greater than or equal to 1 because in my relation all are positive. Now, since C equal Bn and B equal MA, we know C is equal to Bn and B, and the value of B is MA. So in place of B, I wrote MA. Okay. So can I rewrite the statement like this? N multiplied by M and then multiplied by A, MA. And these two are integers. M and N are integers. If M and N are integers, then their product must be again an integer only. Product of two integers is again an integer. So I'm writing some K. I'm writing. For some K must be greater than or equal to 1. Okay, then C is equal to KA, which is this condition, right? Which means AC belongs to R. Check. We assume at the beginning AB belongs to R, BC belongs to R. I got AC belongs to R, which means the given relation is transitive. We know the definition of the transitive. If AB belongs to R, BC belongs to R, then AC must be belongs to R, which is I proved it. That's all. Question 1, part 4. Relation R in the set Z of all integers defined as R equal xy such that x minus y is an integer. Given set Z is an integer. Integers means all negative and positive numbers, which is defined as set Z, and relation R is defined on set Z. So R equal xy such that x minus y is equal to an integer. Is an integer. I cannot, this is in the set builder form. I cannot write this time in the roster form. It is not possible to write it because set of all integers, he said, you cannot write it in the roster form. Now we need to prove this relation R is reflexive, symmetric, and transitive. At first, it is reflexive. For any A belongs to Z, then A comma A belongs to R. How? Any integer, suppose 1 minus 1 equals 0. If it is 0, 0 is an integer. If it is two identical elements of any ordered pair and subtract them, the result is always an integer. That is why it is an integer. Since A minus A is equal to 0, which is an integer, then A comma A belongs to R. So this relation R satisfies transitive condition. Now, symmetric. We know symmetric definition. If AB belongs to R, then BA must be belongs to R. Now, if AB belongs to R, then according to the definition, if AB belongs to R, then A minus B is equal K. For some K belongs to an integer. Of course, if I subtract two integers, the result is always an integer. Now, if I multiply this equation with a negative sign, it will be B will become positive and A will become negative and K will become negative. It will be like this. So B minus A equal minus K. I have multiplied this equation throughout this equation by negative 1. So positive, negative, negative. So B minus A equal some negative K. Negative K is also an integer. So if A comma B belongs to R, then A minus B equal K, and B minus A is equal minus K, which is also an integer. So B comma A also belongs to R, which means this relation satisfies symmetric condition. Now we need to prove transitive condition. This is the given relation and we have to prove this relation satisfies transitive condition or not. Now, if I assume A comma B belongs to R and B comma C belongs to R, according to the definition of the relation, if AB belongs to R, then A minus B equals some integer. If AB belongs to R, okay, then A minus B equal some integer as per the definition, okay. And if BC belongs to R, then B minus C equal another integer. This is as per the definition of the relation. Now we have to check whether AC belongs to R or not. To check AC belongs to R, we have to prove A minus C equal some constant K, where K is any integer. This is what we have to prove. Now, check, we have A minus B equal M and B minus C equal N. This is what we have it. From these two equations, try to solve B. I'm going to solve B here. So b equal, if I switch negative b on the right side and m on my left side, so b will become positive, m will become negative. Similarly on the other side. So b positive, I switched here, m is negative. So b equal a minus m. Similarly, I solve for b. B is here. I switch this negative c on the other side, it becomes positive c. Now I got two values of b. Now on comparing the values of b, a minus m equal n plus c. A minus m equal n plus c. This is what we got it. Now I switch c on the left. So it will become negative, and m on the right, it will become positive. It will be like this. A minus c equal n plus m. Now here, n and m are two integers. You can check. Sum of two integers is again an integer. So I'm saying n plus m as k for some k, and k is also an integer. So a minus c equal k. Check. This is what we have to prove. This is what I proved it. Then a comma c belongs to R. If I prove this one, a minus c equal k, then ac belongs to R. Hence, the given relation satisfies the transitive condition. Question 5. Relation R in the set A of human beings in a town at a particular time given by. Relation R is defined as xy, such that x and y work at the same place. Now we need to check this relation is reflexive, symmetric, and transitive. Relation R is defined on set A to A, where where set A has few peoples, people 1, people 2, people 3, so on. Reflexive. We know the reflexive relation. For any A belongs to R, A belongs to A, then A comma A belongs to R. Which means, try to understand, x, y, here A and A. So which means it's one person. As A works at the same place, which means the other A is also works at the same place. So A and A belongs to R. Symmetry. We know if A comma B belongs to R, then A and B work at the same place according to the relation. If A and B works at the same place, which means B and A also works at the same place, which means B comma A is also belongs to the relation. And we know symmetric condition says if AB belongs to R, then BA must be belongs to R. Hence, this relation is symmetric. Now transitive. Assume A and B belongs to R and B and C belongs to R, which means A and B works at the same place, and B and C also works at the same place, because AB belongs to R, so they work at the same place, and BC belongs to R, which means they work at the same place. The meaning of this one is A and C also works at the same place, which means transitive relation says if AB belongs to R and BC belongs to R, then AC must be belongs to R, which means AC works at the same place. So AC belongs to R. Hence, it is a transitive relation. Part B. Relation R is defined as xy such that x and y live at the same locality. We have to check whether this relation is reflexive, symmetric, and transitive. For any A belongs to A, then A comma A belongs to R, which means if person 1 lives in the same locality, which means person 1 and 1 identical elements, they live in the same locality. So it is a reflexive relation. Now, symmetric. If A comma B belongs to R, which means according to the relation, A and B live in the same locality. A and B live in the same locality as per the relation. A and B lives in the same locality, which means B and A also lives in the same locality. Right? Symmetric definition says if AB belongs to R, then BA must be belongs to R, which means BA must be belongs to R. Hence, it is a symmetric relation. Now, come to transitive. If AB belongs to R and BC belongs to R, according to the relation, if AB belongs to R, which means AB live in the same locality. BC belongs to R, which means B and C live in the same locality. Now, if AB and BC live in the same locality, which means A and C also live in the same locality. Right? What is transitive relation? If AB belongs to R and BC belongs to R, then AC must be belongs to R. So AC belongs to R. Hence, it is a transitive relation. Question C. Relation R is defined as XY and X such that X is exactly 7 centimeters taller than Y. The definition says R equal XY such that X is equal Y plus 7. We have to check this relation is reflexive, symmetric and transitive. Now let's start with reflexive. For any A belongs to A comma A does not belongs to R, because person A and person B person A and person A means one person only, and its height must be the same. It cannot be the taller than by himself. That is what I wrote it. A person cannot be taller than himself. So A is not equal A plus 7. Hence, it is not a reflexive relation. Let us check symmetric. If AB belongs to R, then A equal B plus C, according to the relation. If I solve for B from this equation, B equal A minus 7. B equal A minus 7. Now, if AB belongs to R, then BA here, since B is not equal to A plus 7, then B comma A doesn't belong to R. Because if I say BA belongs to R, then B must be equal to A plus 7, which is not here. So it is not a symmetric relation. Now we need to prove transitive. A transitive relation says, assume AB belongs to R and BC belongs to R. If AB belongs to R, that means A equal B plus C. And BC belongs to R, which means B equals C plus 7. Now from this equation, I'm solving B. So B equal A minus 7. Now equate the values of B. On equating B, A minus 7 equal B C plus 7. I switch negative 7 on the other side. This negative 7 on the other side, it becomes positive 7. So it will be A equal C plus 7. Since A is not equal C plus 7, according to the definition of the relation X equal Y plus 7. So A is not equal C plus 7. Then AC does not belongs to R, which means the given relation is not a transitive relation. Whereas the transitive relation says A, B belongs to R, B, C belongs to R, then A, C belongs to R. Part D. Relation R equal XY such that X is the wife of Y. So here X is wife and Y is husband. Now we need to check, is this given relation is reflexive? For any A belongs to A comma A does not belongs to R. Since A is the wife of B, so I cannot say A is the wife of A. Since I cannot say wife, A is the wife of herself. That is why it is not a reflexive relation. Now we need to check symmetric. If A comma B belongs to R, which means A is the wife of B. And now symmetric relation says if AB belongs to R, then BA must be belongs to R. But BA does not belongs to R. Since B is the husband, so B cannot be the wife of A. So B comma A doesn't belongs to R, does not belongs to R. Hence it is not asymmetric. Now check transitive. Assume A comma B belongs to R, which means A is the wife of B. But B comma C does not belongs to R. Then B comma C does not belong to R. Because if I say if it is belongs, then B is the wife of C. But B is the husband of A. So it is not a transitive relation. B comma C doesn't belongs to R. Part E. Relation R equal XY. X is the father of Y. So X is the father of Y, which means here father is X and son is Y. Now we need to check reflexive relation. Reflexive relation for any A belongs to A comma A does not belongs to R, because A is the father of A. I cannot say A is the father of A. So it is not a reflexive relation. Now check symmetry. If A comma B belongs to R, then A is the father of B. But I cannot say B comma A belongs to R. We know symmetric relation says if AB belongs to R, then BA must be belongs to R. But B cannot be the father of A, because A is the father of B. So here B is the son, A is the father. So it is not a symmetric relation. B comma A doesn't belongs to R. Transitive. If AB belongs to R and BC belongs to R, the meaning of this one try to understand. A is the father of B. A is the father of B. And B is the father of C. So A is the father of B and B is the father of C. But C does not belongs to R. Because A is the father of B, it cannot be the father of C. So we cannot say A is the father of C. So A comma C does not belong to R. Hence it is not transitive relation. Question 2. Show that the relation R in the set R of real numbers defined as R equal AB such that A is less than or equal to B square is neither reflexive nor symmetric nor transitive. We have to prove all these doesn't satisfy us with the above relation. Now at first, what are real numbers? Real numbers are the integers, fractions, decimals, irrational numbers. Whatever represents on the number line, those numbers are called real numbers. Now, given relation R is defined on R, where R is a real number, which means R equal AB such that A must be less than or equal to B square. Now, let us check reflexive first. it is clearly observed that 1 comma 2 1 over 2 comma 1 over 2 does not belongs to R, which means according to the relation half, since half is not less than or equal to 1 over 2 square, because this 1 over 2 square, the value of 1 over 2 square is 1 over 4, which is smaller than half. So 1 over 2 is not less than 1 over 4. So the given relation is not reflexive. Now come to symmetric relation. Let us assume any ordered pair. Let A comma B belongs to R. Then according to the relation, A must be less than or equal to B square. So 1 must be less than or equal to 5 square. Yes, it is true according to the definition. But symmetric relation said if A, B belongs to R, then B, A must be belongs to R. But 5 comma 1 does not belongs to R, since 5 is not less than 1 square. According to the definition, A must be less than or equal to B square, according to the relation. Hence, it is not a symmetric relation. Now, let us prove transitive. A transitive relation says if AB belongs to R and BC belongs to R, then AC must be belongs to R. Now, if AB belongs to R, which means A is less than or equal to B square, and BC belongs to R, which means B is less than or equal to C square, AC belongs to R, which means A is less than or equal to C square. Now, choose any 3 numbers, randomly choose A, B, C values. Consider any values, A, B, C. In this presentation, I choose A as 10, B as 5, C as 3. So you have to choose random numbers that should not satisfy this one. Okay, now let us see. If A is 10 and B is 5, this condition satisfies. Check. 10 is less than or equal to 5 square. 5 square is nothing but 25. So 5 square is 10 is less than 5 square. Yes, this one satisfied. And the second one, B and C. B is 5 and C is 3. So 5 is less than or equal 3 square. 3 square is nothing but 9. Yes, 5 is less than or equal to 3 square. Yes. Now, the third condition, A is less than or equal 10 square. See, this does not satisfy. A is 10 and 3 square is 9. A is 10 and C is 3. So 3 square will be 9. But 10 is not less than or equal 3 square, which does not satisfy the given relation. So the given relation is not transitive. Question 3. Check whether the relation R defined in the set 1, 2, 3, 4, 5, 6 as R equal A comma B such that B equal A plus 1 is reflexive, symmetric, or transitive. Now, let us define a set A equal 1, 2, 3, 4. And relation R is defined on set A, so that R equal A comma B such that B equal A plus 1. Now, check reflexive. For any A belongs to A, then A comma A does not belongs to R. Why? Check. The definition says, the relation says if AB is in the relation, then B equal A plus 1. If A and A is in the relation, then A does not equal A plus 1. A cannot be increased than A plus 1. So on the left I have A and on the right A plus 1. So they are not equal. So it is not a reflexive. Symmetric. We know if A comma B belongs to R, then B equal A plus 1. If I solve for A, A equal B minus 1. Since A is not equal B plus 1, because if B comma A belongs to R, then A equal B plus 1. So B comma A does not belongs to R. Hence, it is not a symmetric relation. Now, check transitive. A transitive relation, which means if AB belongs to R and BC belongs to R, then AC must be belongs to R. Now, see here. If A comma B belongs to R and B comma C belongs to R, AB belongs to R, which means according to the definition, B equal A plus 1. B equal A plus 1. And if BC belongs to R, then C equal B plus 1. Now, solve B from this equation. B equal C minus 1. Now, on equating the values of B, I got A plus 1 equals C minus 1. Now, I switch plus 1 on the other side, it becomes minus 1. So, C equal A plus 2. C equal A plus 2. I switch here. If C must be, since C equal is not equal A plus 1. C must be A plus 1. But here it is not equal. Then AC does not belong to R. Because if AC belongs to R, then C must be equal A plus 1. But here in this case, C is not equal plus 1. A plus 1. It is A plus 2. Hence, it is not a transitive relation.